Hi, I'm Bijan Tabatabai from the University of Wisconsin-Madison, and today I'm going to talk about FBMM, our system to make memory management extensible with file systems. An area that's seen a lot of innovation recently is memory hardware. There's high bandwidth memory, persistent memory that provides persistence and capacity, and more recently CXL, which allows for diverse memory hierarchies and accelerators. This new hardware has inspired a lot of research. Persistent memory and multi-node servers inspired research on how to increase TLB reach and fix other scaling issues for large memories. CXL and RDMA inspired research on how to build disaggregated memory systems, where memory is spread across multiple machines. HBM and persistent memory inspired research into tiered memory, where memory is segregated into fast local storage and slow but remote large storage. Many of these systems require kernel support. One example is Meta's transparent page placement work, which manages memory of a fast local tier and a slower larger tier over CXL. Its aim is to place frequently accessed memory into the fast tier to hide the poor performance of the slow tier, while placing the less frequently used memory in the slow tier to make use of the expanded capacity. First, the kernel is modified to decide where a new allocation should be placed based on the type of allocation and the local node's capacity. Second, the kernel must manage migrating pages between nodes. This also requires a way to track which pages are hard-coded. However, adding kernel support is hard. Kernel memory management code has many branching paths and if-def configs that check for different policies and configurations, making code difficult to follow. This is worse in the kernel than in other software because the kernel must handle every edge case and always fail gracefully. Additionally, policy implementation is spread across many files in Linux kernel, making it hard to find where changes need to be made. For example, in the MM code, there are 48 references to PMD transhuge across 19 files, which checks whether or not a page is huge. Similarly, there are 25 checks for if the kernel is compiled for a NUMA system or not. Currently, to implement a new feature, the implementer needs to have a good understanding of which of these branching paths are relevant and all of the files that they need to change to achieve their goals. For example, TPP modifies 22 source files in its implementation. So the current way of extending memory management is unsustainable. We must make it more extensible. In the rest of this talk, I'll discuss our design to make MM extensible and its usefulness. So to guide our design, we looked at other places in the kernel that provide extensibility, like file systems. The file system interface in Linux is incredibly extensible. Different file systems exist that support different hardware and policies. The VFS layer is what provides this extensibility. It makes the choice of file system transparent to applications. Applications don't care what file system it's on top of, they just use the standard interface to access files. It also allows multiple file systems to exist on the system at the same time if different functionality is needed. And it provides great modularity. There are about 50 file systems in the Linux tree, and many more exist outside the kernel as modules. The kernel also provides many generic implementations of common file system functionality, so implementations can focus on the important changes. The VFS layer can do this by exposing callback functions for file system operations that each file system implements to fit their needs. Then when a file system is loaded, it registers its callback with the kernel, which are used to seamlessly integrate the file system with the generic file system syscalls exposed to applications. This is the model we want to mimic when designing an extension interface for memory management. Interestingly, there's a place in the kernel that uses file systems to extend memory management, HugeTLBFS. HugeTLBFS is a RAM-backed file system used to support huge pages without complicating existing memory management code. Before THP, an application would interact with a monolithic Linux memory manager to handle base pages. However, the application might have a data structure that causes many TLB misses and would benefit from using huge pages. Luckily, HugeTLBFS is mounted to support huge pages. To take advantage of this, the application must be modified to create and map a file in its mount directory for the data structure's memory. These file system operations would trigger the VFS, which would then forward the operations to HugeTLBFS, which contains the logic to support huge pages. This points to a possible general solution to memory management extensibility. It shows that file systems can be used to implement memory management behavior. However, this solution is still lacking as it does not provide transparency to the application. If a user wants an application to use HugeTLBFS, the application must be modified to do so. So looking at the success of HugeTLBFS made us wonder, why create a whole new interface from scratch? File systems provide most of what we want, so let's write memory managers as file systems. We just need a way to get transparency. So how exactly does one implement a memory manager as a file system? Well, memory managers want to do things like physical memory allocation and page placement, virtual memory allocation, and freeing physical memory. Traditional file systems support memory mapping in their files, so the VFS allows file systems to implement various memory management callback functions, such as the page fault callback, which can be used to allocate physical memory. There's also a callback that is used to allocate a virtual memory region, and the callback for file deletion can be used to signal to free physical memory. In addition to being the VFS, file systems are still in the kernel, and therefore can directly access kernel data structures like page tables, and spawn kernel threads for asynchronous work like background compaction. So, as we've discussed, currently all applications talk to the monolithic memory manager. However, since it has to support everything, it's like a big pile of spaghetti of different policies and configurations mixed throughout. Instead, we propose what we call file-based memory management, or FBMM. In FBMM, memory managers are written as file systems called memory management file systems, and memory is allocated and freed through files. Each MFS is a self-contained module of code that is specialized, rather than being a one-size-fits-all solution. These modules can be written and loaded separately from the main kernel, allowing flexibility in their creation and use. The VFS layer is used to multiplex between the MFSs, so applications can have a variety of memory behaviors depending on their needs. So let's go over how FBMM works in practice. First, an application would create a file in its desired MFS's mount directory, call ftruncate to size it, and then mmap. The VFS would process the FS operations and forward them to correct MFS. The MFS would then process the request, and after the mmap completes, the address would be returned to the application. Then the memory is used like it would be normally. At some point, that region may cause a page fault. Again, this is handled by the VFS and forwarded to the corresponding MFS. There, the MFS handles the fault and allocates physical memory if it has not already. The MFS can also perform asynchronous work inside of kernel threads. This includes things like migrating pages. Finally, when the application wishes to free memory, it simply unmaps the region and deletes the file. The deletion triggers the VFS, which forwards it to the MFS, which then frees the physical memory. So if all we did was write memory managers file systems, applications would have to be modified to use them. For transparency, we want applications to be able to allocate and free memory using standard functions like mmap, munmap, and malloc. VFS does not support such a thing, so we add the FBMM shim to the Linux kernel so applications will have to be modified to use FBMM. The FBMM shim translates anonymous memory system calls to file system operations like file creations and deletions, and keeps metadata of open files used for memory. To specify what MFS an application should use by default, the administrator sets an environment variable to a mount directory on startup. Then, when the app calls memory mmap with the mapanon flag, break or munmap, the FBMM shim intercepts the call and creates a file in the default mount directory or deletes the file corresponding to the munmap. The file creation deletion triggers the VFS, which forwards the request to correct MFS. From there, the MFS does what it needs to handle the event, which may include allocating or freeing physical memory. The MFS used by the application can be changed without modifying the application itself, just by changing the environment variable used on startup. So let's talk a bit about how the FBMM shim manages the MFS files it creates. Naively creating a new file for each memory region would be prohibitively expensive. Therefore, to amortize the cost of creating files, the logical size of each file is set to 128 gigabytes, and multiple allocations are placed inside the same file. Making a file this large is only a metadata operation and does not incur any significant cost. To organize the MFS file, each file is associated with a virtual address range of the same size of the file, which represents where that file can be mapped. The MFS files created by the shim are stored in a per process tree indexed by the virtual address range that is associated with the file. When an application makes a call to mmap or break, the FBMM shim will search the file tree for the MFS file whose virtual address range fits inside the virtual address range of the new allocation. If such a file exists, that file is used for the allocation. If a suitable file does not exist, a new file is created and added to the file tree. While transparency is nice for general purpose applications, more sophisticated applications may want more control over their memory management behavior. With Linux currently, the application control is limited to the options available to the mmap and madvise system calls. However, with FBMM, an application can choose to use an MFS that has the exact policies it wants. For example, imagine an application that runs on a machine with tiered memory that migrates pages and has a specific memory region that is used for DMA and therefore must be pinned. The application can allocate most of its memory from the tiered memory MFS using the transparent FBMM shim. However, for the DMA region, it can manually create and map a file in the pinned memory MFS, bypassing the shim to provide the needed functionality. By doing so, the application must also take on the responsibilities of the shim for such files, such as deleting them when they are no longer being used. The usage for this is like using huge steel BFS. Now let's look at the overhead of using the FBMM shim. Because the shim does its work on the memory allocation path, we evaluate this by creating a micro benchmark that measures the amount of time it takes to map a bunch of regions. We use a bare bones MFS to evaluate this. We measured that on average, the FBMM shim adds an additional 150 nanoseconds to a call to mmap. If no physical memory is allocated, this amounts to about a 20% overhead. However, the cost of allocating and zeroing physical memory dominates the time spent creating a memory region. With only 16 physical pages allocated, this overhead drops to below 1%. To see how impactful this overhead is, we recorded the frequency that different applications request memory from the kernel, which we show in this table. Note that this does not include the number of individual calls to malloc, because multiple malloc allocations often use the same kernel allocation. The workloads we tested request memory from the kernel vary infrequently, limiting the performance impact of the FBMM shim. Even Keneal, which makes allocations the most frequently, in the set by far, would only suffer a handful of microseconds of extra delay per second. Now that I finished explaining the design of FBMM, let me give a brief example of how we used it to create a basic MFS. All this basic MFS does is pre-reserve its physical memory from the kernel on startup to simplify allocation, allocates virtual memory addresses to new memory regions, allocates its pre-reserved physical memory to applications when the page is first touched, and frees the physical memory when it's no longer being used. To implement this, we implement the physical memory reservation inside the fill super callback, which is called when the MFS is first mounted to set up the file system. We use the default implementation of the get unmapped area callback to assign virtual addresses to new memory regions. We give physical memory to processes during the page fault inside the fault callback, and we free physical memory when a file is deleted in the free inode callback. So what more complex MFSs can we build with FBMM? To show the expressions of FBMM, we created 3 different standalone MFSs. Tiered MFS implements a tiered memory system inspired by the TPP work described at the beginning of the talk. Bandwidth MFS efficiently uses the memory bandwidth available on a system by interleaving the memory across the NUMA node with user-defined weights. Finally, config MFS attempts to allocate the physical memory as contiguously as possible. Let's take a deeper look at the implementation of tiered MFS. We implement the page fault callback to make placement decisions based on the available memory in the local node. And we start kernel threads inside the fill super callback to periodically perform hotness tracking and migration. Hotness tracking involves scanning page table access bits, and migration is done by allocating a page in the destination node, copying the page, and then updating the PTE. We tested tiered MFS by running memcached with about 40 gigabytes of memory with YCSB using a Zipfian distribution and measuring the throughput in 3 configurations. The section labeled Linux is base Linux with all the memory in the local node. Linux split is base Linux with 8 gigabytes of local memory and 64 gigabytes of remote memory. And tiered MFS is our system with 8 gigabytes of local memory and 64 gigabytes of remote memory. Because we found the throughput to be somewhat noisy, we ran the experiment 50 times and showed the Boskin whiskers plot of all the runs. The median throughput of tiered MFS is 98 that of base Linux, while the median of Linux split is only 94% of base Linux. Additionally, the tail performance is better in tiered MFS than with Linux split. Tiered MFS is able to perform better than Linux split because its tiering functionality only allows 0.5% of the memory accesses to go to the remote node, compared to 57% in Linux split. For bandwidth MFS, we want to interleave memory allocations between NUMA nodes to use their aggregate bandwidth. By default, bandwidth MFS will interleave the memory evenly across the NUMA nodes. However, each node may have different access characteristics. So in the fill super callback, it also exposes a sysfs interface, allowing the user to modify the interleave weights for each node. To perform interleaving, we implement the page fault callback to allocate memory across NUMA nodes in a round-robin fashion, weighted by the interleave weights supplied by the user. In this example, the first 3 pages are allocated in node 0, the next 2 in node 1, and the next in node 2. This pattern repeats for subsequent allocations. To evaluate bandwidth MFS, we ran the stream micro benchmark using it with different interleave ratios to measure the used memory bandwidth. In this figure, the ratios are written as local node weight, remote node weight. The Linux label uses the default Linux memory manager, which keeps all the memory in the local node. The bandwidth usage varying with the interleave ratio shows that bandwidth MFS is indeed interleaving the pages at the desired ratios. and that interleaving with the correct ratios can increase the bandwidth available to applications. Finally, the goal of contig MFS is to make physical memory as contiguous as possible. For example, say a new memory region is created using a mmap that is 6 pages long. There are already some allocated pages, fragmenting memory. Contig MFS will allocate physical pages in the regions 4 pages long and 2 pages long, ignoring the region that is only 1 page long. Because allocating a physical page when the page is first touched can lead to fragmentation, all the physical memory for a region is allocated at the same time as the virtual memory inside of the get unmapped area callback. The virtual to physical mappings are still managed inside the pagefall callback. To evaluate contig MFS, we tested with a simulated range TLB, where a single TLB entry caches translations for an arbitrary range of contiguous pages. Allocating memory contiguously with a range TLB is beneficial because the more contiguity allows an application's address space to be represented in fewer range TLB entries. We measured how many TLB misses were saved using contig MFS and range TLBs compared to a traditional TLB with base pages. The results are shown in this table. Because contig MFS effectively allocates memory contiguously, it helps the range TLB reduce the numbers of TLB misses drastically. So does implementing memory managers as MFSs make them easier to write? It's hard to quantify exactly how easy it is to write code, so we will use the imprecise metric of number of files and lines changed as a proxy. To implement tiered memory, TPP modifies 22 different kernel files and modifies 471 lines of code. Our implementation of tiered MFS spans 3 independent files and is around 1,500 lines of code. About a third of this is from boilerplate and debug code, and the rest of the increase is due to implementing hotness tracking and page migration inside the MFS, while TPP integrates itself inside the kernel and is able to piggyback off it for these tasks. We believe that the modularity outweighs the cost of these implementations, and had we used something like daemon for hotness tracking instead, the number of lines would also have decreased. HMSDK is a system from SK Hynix which provides bandwidth expansion through memory interleaving, similar to bandwidth MFS. Due to being implemented as an MFS, bandwidth MFS requires changing fewer lines and files. The same is true for contig MFS and RMM, a previous system that implements contiguous allocation inside the kernel memory management code. See the paper for more details on each MFS. So, in conclusion, the current way of extending memory management by adding to the monolith is not sustainable. We also do not need to completely redesign the memory management system to support extensions. Writing individual memory managers as file systems with FBMM is the best way forward. Thank you.